you can see on the board. So this is a summary of the question. So if you can download the exam from the Moodle page, this is question 3 in 2014. And so U is the temperature, okay? And U is a function of X and T. So X is space and T is the time variable. And X is the length of the wire, and it just goes from 0 to capital L, okay? And T is the time, so it goes from 0 to capital T, yeah? And then we discretize the domain. So we discretize the domain by xj, yeah? So xj is just j multiplied by delta x. So delta x is the space step, like you divide 0 to L into equivalent space, and each subinterval has length delta x. Similarly, you divide the 0 to t into m intervals, and the length of each subinterval is delta t. So then at xj and tl, we have the exact solution u xj tl, but then you want to approximate the exact value by ulj, okay? So here then we will solve the discretized equation, okay, by this formula. So this formula is given in the question, okay? So look at this one. So U, so this is a vector, right? It contains the values of, like on the j from 0 to n plus 1, yeah? And then at l plus 1, so it's a vector. And this one is a vector as well. And A is a matrix, okay? And delta t is the time step, delta x is the space step, okay? So now we go to the question. So question A, little a, say that what additional information you need to specify this problem. So the additional information is we need the boundary condition, okay? And the initial condition. So what are the boundary conditions? So boundary conditions are the values of u, when x equals 0, or the value of u when x equals capital L, okay? And what are the initial conditions? So initial condition is the value of u when time equals 0, okay? And so move to question B. So it says that so this equation is labeled 3.2 in the question, okay? So let's say that on the left hand side of 3.2, so this one is the approximation of a derivative with respect to time. So the question is, what is the order of accuracy of this approximation? And you see, you look at the formula and you compare with the formula given in the exam paper. So there is 3 formulas for finite difference approximation in the paper. So this one is just the approximation of first derivative, okay, using forward difference scheme. And you can see that, the forward difference scheme, the order of approximation is just 1, or, O delta t. So this one is order 1, okay? And now question C. So look at 3.2 again. Okay. So let's say that is it an implicit method or explicit method? Yeah. And give a reason. So if you look at 3.2, you see on the left and on the right hand side, on the left hand side, you see L plus 1. Okay. So L plus 1 is unknown when UL is given. So in this case, we call it the implicit method. Okay. So it's an implicit method. Because UL plus 1 is on both sides of 3.2. Okay. And then what is the advantage of implicit method compared to explicit method? So the advantage is it's more stable. Okay. And does not require the condition on delta t over delta x squared has to be less than some constant. Okay. So that is the advantage of the implicit method. Okay, so now we move to question E. So question E, now you are given the boundary condition. So boundary condition is U at 0 and U at capital L, t equals 0. Okay. So now you have to identify the matrix A. Well, you have to identify the first, the second row, and the last row of the matrix A. Okay, so the question is, so what is the first row of the matrix A? Okay, and then what is the second row and what is the last row? So this question is a bit tricky. So before, we can say what is the first row of A, what is the second row of A, what is the last row of A. We have to look at this equation, okay, more closely. And now, if I can erase the bit here, so we just look at 3.2 once again. Okay, and now if we write down in terms of component by component, okay, so this one is U L plus 1 minus UL, but now instead of writing the vector, I write the entries of the vectors. Okay, so the entries will be uj and subscript L plus 1 and divided by delta t. Okay, and so on the left hand side, you use a forward difference scheme. Yeah, so you have this approximation. So on the right hand side, so remember that the question says that you have to use central difference scheme to approximate the second derivatives. So then, because you use central difference scheme, so you have uj plus 1 L plus 1 minus 2uj L plus 1 plus uj minus 1 L plus 1 divided by delta x squared. Okay. But you see, now we have to be very careful. So here J run from 1 to n only. Okay? Because, you know, remember we have maximal is J plus 1 here. So it can be n plus 1. Okay? And here you have J minus 1. So when J equal 1, this one can go to 0. Okay? So that's what we say. So when J equals 0, then U0L, okay? So because the index J equal 1, so you got U0 here, and L will equal U at x0, and the time is TL. So remember ULJ approximate, you know, the value at UXJ and TL, and in this case J equals 0, so it approximate, you know, UX0 and TL. But now we have to use the boundary condition. Okay, so the boundary condition say that when x equals 0, U is just equals 0. So you just put this one equals 0. Yeah. And then when J equal n plus 1, so this one is at one end. So how about at the other end? So at J equal n plus 1, then you have U n plus 1 L. Okay. So, well, this one, because we know the exact value, so we just make it exactly equal. Okay. Because we know the boundary condition. So here is U at xn plus 1 TL. Yeah. And then, you know, you have this one is just U at capital L T, and by the boundary condition it just equals 0 as well. Okay. So now we look at this equation again. Okay. So now I just leave 3.2 just untouched because we want to find out what is the matrix A, at least the first, the second, and the last row. Yeah. So now, if J equal 1, yeah, then this equation, so maybe let's say this one is star. Star is reduced to, so now you just put in J equal 1. Okay, so you put J equal 1 into this equation. So what did you get? So you get U1 L plus 1 minus U1 L divided by delta T equal U2 L plus 1 U2 L plus 1 minus U0 L plus 1 divided by delta X squared. Right? So now, so remember this one, you know, is true for all L. So this one is true for all L. Yeah. So therefore, this term goes away. So this one goes away. Okay. No, I'm sorry. This one should be 1 because J equal 1. So this one should be 1. Yeah. Okay. So this one, if I write down explicitly, so this one is just 1 over delta X squared. Okay, and then I have minus 2U1 L plus 1 plus U2 L plus 1. Okay. And now you compare 3.2 and this one, this equation. And then you can see that the first row of the matrix A. So the first row of the matrix A. So compare say maybe this one is double star, yeah. So compare double star and 3.2. Then you can see that the first row of the matrix A of A will be what? So you see, now you look at this one. So this one is a matrix A multiplied by a vector. And what is the vector? So the vector U is just, U1, U2, U3 up to UN. Okay? And here you see that you see only U1 and U2. So the rest is just equal 0. Yeah? And then because we have a minus here, okay? So then we just take only 2 here and then minus 1. And then the rest is just equal 0. Okay, so this is the first row of the matrix A. You see, because you compare 3.2 given by the question, and double star is when you work it out explicitly. And that you can see that the matrix A, the first row has to be 2 come from here, and minus 1 is the coefficient from here in front of U2, and 0 because there's no U3, U4 up to UN. Okay? And you can do the same for second row and last row. So for second row, so you just take J equal 2, okay? And then star is reduced to so you just take this equation and you put J equal 2, okay? So you got U2 L plus 1 minus U2 L plus 1 divided by delta T equal U3 minus 2 U2 minus or plus. So I forgot this is a plus, so this one should be a plus, yeah. Plus here, so plus here, so plus, yeah. And U1 L plus 1 divided by delta X squared. Okay. So again, we use the same trick. So you compare, say this one is triple star. Okay, so you compare triple star with 3.2. So if we compare triple star with 3.2, yeah, with this 3.2, then you get the second row of the matrix A. Okay, so the second row of the matrix A. So I'm sorry because this one is not easy to see, so I just go a bit up, yeah. So I want to erase this. So then the second row of the matrix A is, you just look at this one. So the coefficient in front of U1 is plus 1, but we have a minus here, so we would have a minus here. The coefficient in front of U2 is minus 2, and there's a minus here, so we just put 2 here. Okay, and then for U3 it's a minus 1 here, and the rest is just equal 0. So this is a second row of the matrix A. Okay, So how about the last row of the matrix A? Well, so the last row of the matrix A. So the last row we just take j equal n. Then you have this equation again. So u n, so L plus 1 minus u n L over delta t. And then you have u, because j equal n, so you have n plus 1, L plus 1 here, minus 2n L plus 1 minus u n minus 1 L plus 1 divided by delta x squared. Okay? And now remember we discussed the boundary condition. Yeah, so the boundary condition, you know, will make this term goes away. Yeah, so this goes away because the boundary condition. We discussed it before. And so now the last row of the matrix A. So now then I can erase this, yeah, because now we know what is going on. So the last row of the matrix A. So you have a lot of zero in the front, okay? And in the very last, well, only the second last entries, you have a, you know, 1 for un minus 1, okay? And 2, or should be, there's a plus here again, so there should be a plus. So minus 1 for un minus 1, and 2 for the last un, okay? So this is the last row of the matrix A. So before it, you just have a lot of zero. Okay? So now, once you know the matrix A, you can answer the next question. So the next question is, suppose the vector v is given like this. So 1, 2, 3, 4, 5, up to n. Okay? Then we have to compute, you know, the MATLAB commands. So I just do the command step by step. But the first is you take v dot hat 0. It just means that you take every element inside the vector v and you raise to power 0. Okay? So if you raise everything to power 0, just get 1. 1, 1, 1 to the n. Yeah? And now the next command is the vector w is given by a, the matrix A, we found it in the previous question, multiplied by v dot hat 0. Okay? So remember the matrix A we found the previous question. It's look like this. So you have 2 minus 1 in the first row and 0, 0, you know, until the end. And for the second row, you have minus 1, 2, 1, and 0, 0 up to the end. Okay? And here you have 0, minus 1, 2, minus 1. So you see the pattern, minus 1, 2, 1, minus 1, 2, minus 1. So there should be minus 1 here. Okay? And then the very last row, you just have minus 1 and then 2. Okay? And then now you multiply with this vector. So actually this vector should be a, you know, I mean should be a column vectors because there's a transpose in the very end. Yeah, so there's a prime in the very end. So then you just have to multiply this matrix with 1, 1, 1, 1 up to the n. Okay? And the question just asks you what is the second entries. Yeah, so what is the second entries of the results? So the answer is just W at 2. So what is the second entries, yeah, of this product? And you can see that in order to find out the second entries, you just take the second row of the matrix, right? You just take the second row of the matrix and you multiply with the whole column vectors. Okay? And now you see it easy. Now you just take -1 multiplied by 1, 2 multiplied by 1, -1 multiplied by 1. So just give you 0. Okay? Because you got -1, then 2, then -1, just give you 0. Yeah? And so now the next question is, what is A multiplied with V dot to the power 1? So we take the vector V, okay, and you just raise to the power 1, which is just exactly the same. 1, 2, 3, up to the last value. Okay? And now we compute W equal A times V raised to the power 1. So what is 2 minus 1, 0, like -1, 2 minus 1, 0, -1, 2 minus 1, and you just multiply with the vector that has 1, 2, 3 up to n. Okay, and you see again, so this answer 1 just asking you what is the second entries of the product, and in order to find out what is the second entries here, you just take the second row and you multiply with the vector. Okay, so you just take the second row and you multiply with the vector and you get out the second entries. And you see, because there's a lot of 0 in the end, so what you need to do is you just need to take only the first 3 entries. Yeah, so the first 3 entries, so you got -1 multiplied by 1, yeah, is -1. So -1 multiplied by 1 is -1, and 2 multiplied by 2 just gives you 4, and then -1 multiplied by 3 just gives you -3. So this one gives you 0 as well. Okay. And similarly, the last bit is you take V to the power 2. Okay, so you take V to the power 2. So now I reuse this one, but I just change it to the power 2. Yeah, so I just change it here. So if I have to the power 2, then I have 1 square, just 1, 2 square, just 4, 3 square, just 9, and so on. So we don't worry to the very last one. So you got 1, 4, 9, and so on. Okay. And again, now I'm interested only the second element of the results. So I just take -1 multiplied by 1 gives you -1, and 2 times 4 is 8, and then minus 1, 9, minus 9. So this one is minus 2, right? Okay. So that is question number 4. And now what is number 5? So number 5 is, suppose now you have the initial condition. So yield when time equals 0 is just 1 minus cosine x 2 pi over L. Okay? And now they say that at time equals 0, what is when L equals 0? So what is the full equation 3.2? That's corresponding to the first row of the matrix A. So this one, if you look back at 3.2 again, then you can write 3.2 like this. So U, the vector U at L equal 1, yeah, so sorry, L equals 0, then you just have L plus 1 just equal 1, and L equals 0 here, divided by delta T equal minus A U1 divided by delta x squared. Okay, but you see in this case U0 is known. Okay, so U0 is your initial condition. It's just U at xj and at time equals 0. Okay, and what is given? Okay, so you just have 1 minus, so this one is a vector, right? So j run from 1 to n. So you just have to put in, 1 minus cosine, so xj 2 pi over L, and j run from 1 to n. Yeah. And if you remember xj in the very beginning, so xj is just given by j multiplied by delta x, yeah, and j multiplied by delta x, so delta x is just equal L over n plus 1. Then you can simplify this one a bit more. Okay, so then it's just 1 minus cosine, you put xj here, so you got 2 pi j divided by n plus 1, j from 1 to little n. See, because the capital L here cancel with the capital L here. Okay, so this is when you know the initial condition, then you know the vector u0, and from this equation you can get u1, the vector at time equal 1, sorry, at L equal at time equal t1, and then you can use this equation again and again, and you got u2, u3, until the end. So that is the ideas of the method. So now the next question is, for n equal 20, what is the sparsity of the matrix A? So how do we compute sparsity of the matrix? So suppose n equal 20. So what is the sparsity of the matrix? So for n equal 20, so remember the matrix look like this. Two minus 1, 0, 0, 0 to the n, and minus 1, 2, minus 1 to the n, and then minus 1, 2, minus 1, and then 0, 0 to the n, you know. So then the last one is minus 1 and 2, okay? So what is the number of non-zero elements? So what is the number of non-zero element? So you say that the first row has only 2 elements, 2 non-zero elements. The last row has 2 non-zero elements, okay? So the one in the middle has 3 non-zero elements, so 3, and then you have 18 rows in the middle, yeah? So then I just have totally 58 non-zero elements. And the sparsity of A is just 58 divided by 20 square, because the size of the matrix is 20 square, okay? So just give you 14.5%, okay? So now the next question is, so do you expect the inverse matrix to be very sparse? And the answer is no, okay? So A inverse, you know, even you have a sparse matrix like this, when you compute A inverse, it will not be sparse, okay? So we just say that no, it's not going to be sparse. And now the next question is, if A is B transpose B, then prove that A is positive definite. Okay? So before I compute this, before I write the answer of this question, let me check the questions. So whether I have any questions here. So one question says that shouldn't the matrix elements be minus 2 and 1? Well, so somebody answer because there's a minus in front of the matrix A, so therefore, you know, we need to negate the size of the matrix, okay? The sparsity should be given in percentage. Well, it depends on the question, but you know, I mean, if you write down sparsity, if you write down either in percent like this, or you write down like 0.014, it's still okay. Okay, make sure that you got the ratio correctly. Yeah. Okay. So the next question is, you know, how do I prove that A is positive definite? So this question we've seen it in the past exam, I mean in the midterm exam already, but I just want to repeat. Okay, so suppose A is B transpose B. Okay, then to prove A is positive definite, you just take the definition. So if I take a vector X transpose A times x, then I have x transpose, I replace A by B transpose B x. Okay, then this one is just bx transpose bx, and this one is just bx norm to square. Okay, and this one is greater or equal 0 for all the vector x in Rn. Okay, and then in M, yeah, in M, Rm. And now the next step is you need to show that when bx equals 0, then the vector x has to be equal to 0. Okay, and here if you look at the question, say that B has independent columns. Okay, so x has to be equal to 0 because B has independent columns. Okay, so that is the condition that force the vector x has to be equal to 0. So therefore A is positive definite. Yeah. And the last question is, well, not the last one, the second last is, suppose that A has a Cholesky factorization. A is R transpose R. Then how do you solve AX equal B? So how do you solve AX equal B? So AX equal B will be replaced by R transpose RX equal B. And you can solve this one by 2 steps. So you solve, maybe let me just get a space here. So here you just solve R transpose Y equal B, then R, so you take this one to be the vector Y, yeah, then Rx equal Y. So you can solve this one by forward substitution and this one by backward substitution. So it will take about ON square number of floating operation for forward substitution and backward substitution. You try to solve by Cholesky factorization. Okay. So the very last question is, now you go back to 3.2 again. So 3.2 is so 3.2 is given like this. So on the left you have the discretization in time, and on the right you have the discretization in space. Okay, but now you see, in order to solve this, right, now we have to rearrange so that on the left you have only UL plus 1. And on the right, you have UL. Okay? So we just rearrange it. So rearrange it, you have UL plus 1, 1 over delta t. So then you take this one, move to the right, so you have a UL plus 1 divided by delta x squared equal UL delta t. Okay? And you see this one, you can take UL plus 1 to be the common factor. So you have 1 over delta t multiply with the identity matrix plus a 1 over delta x squared, the vector UL plus 1 equal UL 1 over delta t. Okay? And you can simplify delta t. So if you simplify delta t, then what you have, you just have identity here, and you have delta t divided by delta x square a UL plus 1 equal UL. Okay, and this is the form, the matrix K multiplied by UL plus 1 equal UL. So you see, this one you can put into MATLAB because U0 is given. Then using this equation you can solve for U1, and then from U1 you can solve this equation to get U2 and so on, right? And this is a matrix K. So K is I plus delta t over delta x squared multiplied by the matrix A. Okay? And if you have delta t equal 0.1, delta x equal 0.5, then you can figure out what is the coefficient here explicitly. Okay? So that is the question about PDE in the 2014 paper. So now I want to move to 2013, the last question as well, the question on PDE. So let me erase this one. So in 2013, okay, and we look at the question for the PDE. So in this question, now you have to consider the two-dimensional diffusion equations. So U now is a function of x and y. And so what is the region? So now the region is a rectangle. Okay, so the rectangle is given, the pictures is given in the exam, and here you have x run from 0 to 2 and y run from 0 to 1. Okay, and then you just cut this one into 10 equally spaced. So anyway, you can see the pictures in the question. Okay, so h is just 1 over n, and xi is just I times h, and I run from 0 to n, and yj equal j times h, j run from 0 to n. Okay, so you see, like in the previous question, you have two variables, one in space and one in time. But in this question, you have two space variables, x and y. So x is in the x direction and y in the y direction on the plane. So this one is the region omega. Okay. And so make sure that you see that the discretization here, the width in the x direction and in the y direction are the same. So little h is 1 over n. So you just have a equally spaced grid. Okay, so I just draw very rough pictures, but you can see the pictures in the question. And again, so what is extra information you need? So here we need the boundary condition. Okay. Yeah. And now we need to come up with the discretization, okay, of the PDE. So now in the question you are given the forward difference, central difference of the first and the second derivatives. Okay. And now, the question asks you, what is the approximation by central difference of the second derivative with respect to x squared? And then evaluate at xi, yj. Okay. So you just look up the formula given in the question, and you can write out this one. It's just u at xi plus h yj minus 2u xi yj plus u xi minus h yj, and everything divided by h squared. Okay, plus or h squared. Yeah. So that is the central difference approximation for the second derivative with respect to x at xi yj. Okay. And now the second one is, what is the second derivatives? What is the approximation of the second derivative with respect to y? Okay. Evaluate at xi yj. So now you do the same, exactly the same, except that now instead of given the approximation in x direction, now given the approximation in the y direction. Okay, so now you just have u and xi, then yj plus h minus 2u xi yj, then plus u xi yj minus h divided by h squared, and plus OH squared. Okay. So now we want the approximation of the equation. So remember, so now we go back to the equation. So remember uij, you approximate the value at xi, yj, okay? And then xi plus h, it's just xi plus 1, right? Because equally spaced, so xi, you just plus the gap, the width of the intervals, give you the next point, okay? And then similarly, yj plus h is just equal yj plus 1. So you combine those information from here and here, you put into the original PDE, then you get ui plus 1j minus ui comma j plus ui minus 1j divided by h square plus ui j plus 1 minus ui j minus 1 divided by h square equals 0. Okay, so here this term, yeah, so this term, it comes from the approximation of partial u with respect to x square, yeah, and then you see you just replace xi plus h by xi plus 1, and you replace u at xi plus 1 yj approximate by ui plus 1j, okay, and you get this one. And similarly, this term comes from, you know, the second approximation, the central difference approximation of the second derivative with respect to y, okay? And then you just rearrange it. So you rearrange it and you change the sign, you know, from minus to plus, then you get for uij, right? And then minus ui plus 1j minus ui minus 1j minus uij plus 1 minus ui j minus 1 equals 0. Okay, so this one is the form in the question, and so beta has to be equal 4. So beta is 4. Yeah. So if you look at the question, this is the equation given in the question. Well, with beta, okay, and we replace beta equal 4, and we derive it just by putting the correct approximation formula. Okay. So now the next question is, now you need to write down this equation at very specific points. So at x5, y2. So at x5, y2. So here's mean that I equal 5 and j equal 2. So you just need to write down this equation explicitly. Okay? So you just have 4 u5 2 minus u6 2 minus u4 2 minus u5 3 minus u5 1 equals 0. Okay? And the next question is at x9 y1. Okay, so here I equal 9 and j equal 1. Then you have 4 u9 1 minus u10 1 minus u8 1 minus u9 2 minus u9 0 equals 0. Okay, But now we have to pay attention. Okay, if you look at the pictures in the question, yeah, then you can see that this one is on the boundary. Right? U10.1 is on the boundary, and U9.1 is on the boundary as well. Okay? So because it's on the boundary, then we have to use the boundary condition in order to figure out what are the values U10.1 and U9.1 explicitly. Yeah. So U10.1 will be U at x10 y1. Okay, and x10 is the end of the x domain, so just U at 2 y1. And you check the boundary condition given in the question. This one is just equal 20. Okay. And now how about this one? So U90. So U90 is U x9 y0. Okay. And what is y0? So y0 is just 0. And you look at the boundary condition again. So this one is given by 10 times x9. And 10 times x9 just 1.8. So just multiply by 1.8 by 10, so you got 18. Okay. So now you have to rewrite this equation. So you got 4 U91, yeah, minus U81 minus U92 is just equal 38, because you move 20 and 18 move to the right. Yeah, so you got 38. Okay, because those values are knowns, so you have to move it to the right hand side. Okay. So, any question? Any questions? So, yeah. So now the next question is, what is the sparsity of the matrix A? So the sparsity of the matrix A is just the number of non-zero elements of A divided by the total numbers of elements in A. Okay. So now, how many non-zero elements? So now if you look at the pictures given in the exam paper, okay, so if you look at the pictures given in the exam paper, yeah, so if you look carefully at the pictures in the exam paper, you see that the number of non-zero elements is given here in the figures. Okay, so just 154. Okay. And now how do we figure out the number of elements? So the number of elements in A, so is, like, because if you look at the figures again, you have to figure out what is the number of unknowns. So the number of unknowns equal the number of interior points in the discretization. Okay, in the discretization. And again, you can count, like if you look at these pictures, so this is pictures is given in the exam paper as well. Yeah, so you can see that you can count the number of interior points, and it's just 36 interior points. So then this one is 36 times 36 So it gives you the opacity is just 11.88%. Okay. So the next question is, why is calculating A inverse is not a good idea? So calculating A inverse is expensive, right? So calculating A inverse is expensive, and A inverse is dense. Okay, so we don't recommend to compute A inverse explicitly. And now from the pictures, like why we can say that A is positive definite. So okay, you can see that from the pictures given in the question. Yeah. So A is positive definite because A has Cholesky factorization and all the eigenvalues of A are positive. Okay. So A has Cholesky factorization and all eigenvalues of A are positive. Okay, so therefore the matrix A is positive definite. So explain how to use Cholesky factorization to solve the linear system. So this one we've seen it in the previous question already, right? I mean in the previous past exam papers. So you just replace A U B by R transpose R U B, and you solve it in two steps. So you solve R T Y equal B, and then R U equal Y. Okay, by substitution. So the last question is, what other structures does A have that could make solving a linear system more efficient? Well, here, you look at the structure again, you can say that A is sparse. And it has non-zero elements on the diagonals. So we can make use of this structure to derive a more efficient solver, but we are not going into details. Okay, so I just review the solution of two questions on PDEs on the past exam papers. Okay, so I will post the solution on Moodle, and hopefully you will find useful for your exam. Okay, so thank you, and I will stop the live streaming now. Well, unless you have any question, I'll just check the question.